formula we want to remember for today. Okay, and we ended with this on Monday, is KW. K is for constant, W is for water. Okay, and because water is considered to have be an activity or be always 1, then and H plus, the same thing as hydronium, right? H plus and H3O plus. So you can write it either way. Okay, and does anybody remember what this number is, what it's equal to? Nope, it's up here. 1.0 times 10 to the negative 14. So you have to know this. This is our first one, and we'll add to this today. Okay, if we know the concentration of one of these, then we can always find the other one, right? Okay, so if you're given, the first part of this chapter 18 is all strong acids and bases. Okay, if you're given the molarity, so big M there for HCl, okay, it's a strong acid, right? Okay, so if we look at it, a strong acid means it completely ionizes, correct? Okay, so if you have 0.050 molar HCl, then how much hydronium do you have? The same, right? Because it's going to completely ionize. Okay, so whenever you're given the concentration of a strong acid, that concentration is your hydronium concentration. Okay? Same for a base. So if you were given the hydroxide concentration for a base, a strong base, then it would just be equal to that number that you're given there. Okay, so we didn't have to really calculate. This is just showing you why. Okay, so the hydronium concentration is 0.050. Okay, and so I tell you that here. If you're given the molarity of a strong acid, strong base, then that's the concentration. Okay, so if we're given 0.050, and then this is just written in scientific notation, doesn't matter which one, okay, we can rearrange and we can find hydroxide because it's always equal to 1.0 times 10 to the negative 14. So if we rearrange to solve for hydroxide, it's always going to be equal to KW divided by 0.050 or 5.0 times 10 to the negative 2, whichever one. Okay, so all I did was just rearrange the equation to solve for hydroxide. Okay? So when we do that, we should get the 2.0 times 10 to the negative 13 molarity. Okay, you can check this. If you plug in 2.0 times 10 to the negative 13 and 0.050, what should your answer be? 1.0 times 10 to the negative 14. Exactly. And so all this was a rearrangement. If I isolate hydroxide by itself, that means I divide through by my hydronium or H plus concentration, which is what we know because that's what we're given. And so it gives you that. Okay, any questions on that? Just a simple rearrangement. Divide by the number you're given. Yep. And if it was the opposite, so say we had a base instead of an acid that we were given, same thing. You take 1.0 times the negative 14 and divide by the hydroxide concentration of the base. And that would give you the hydronium concentration. Okay. Still looking at strong acids and bases. So I have that in bold here. I'm going to add a couple more equations here. Okay, one of the convenient ways for us to express acidity, really, we usually use the pH scale. Okay, P just stands for power. So power of H. Okay, so power of a proton. Okay, when we think of a proton, do we think of an acid or a base? Acid, right? So we're looking at the power of the acid. Okay, if you look at the POH scale, it's still, vaguely similar. It's just you're looking at the power of hydroxide. Okay, but typically, like I said, you normally look at the pH scale. Okay, so we mentioned that the pH scale runs from 0 to 14. 7's neutral, below 7's acidic, above 7 is basic. Okay, there's a number of ways that we can go about detecting pH. So you guys have used pH paper, right? There's also universal paper, so there's more sophisticated pH paper than what you use. One of our pH papers that's universal, So you would actually, take whatever your sample is and you'd put it on the paper just like you do with the litmus paper. And then you go match it up. There's a color code. It actually will tell you roughly just about what the pH is. Okay, so we don't have that on our litmus paper, right? It just is red or blue. Okay, but you can actually go match it up, and it may be orange is about a pH of 6. So you actually can know more about what the exact pH is. Okay, we can also use pH meters. We don't have those for the lab for everybody. We have the computer that will hook up, so there's a probe, just like we did with the temperature probe, the first lab of the semester. So you can put the probe in there, and it'll read the pH. So that's another way that you can do it. Okay, so the pH, okay, to find this, you're going to take the negative log of the hydronium concentration. Okay, this is also H+, so I'm confused, which makes sense. If you're looking for the power of H, you need to use the hydronium, or the acidic, component here. Okay, POH, you're going to take the negative log of the hydroxide concentration. So POH goes with the base, pH goes with acid, if you want to think of it that way. Okay, so here's just a table to show this. So if we take the negative log of the hydronium concentration of 1, you're going to get 0. So there's the pH. Okay, so if you have your calculator out, I encourage you to plug those in and see that. Okay, if you take the negative log of the 1.0 times 10 to the negative 14, you're going to get a POH of 14. Okay, so you can move on down and see that. So this would be really acidic, right? And then this would be basic, because your pH here is now 14, okay, and so your POH is 0. So you're going to have, so the lower the number, even for the base, so for the POH, the lower the number, the more basic, if you're looking at the POH scale. Okay, but we typically, like I said, look at the pH, and so if you have a 0, then that means it's very acidic, whatever the solution is. Okay, I'll let you play with that for just a second. Okay, and notice, so another key thing we have here, so I'm going to add the formula up here. If the pH scale ranges from 0 to 14, right, then POH plus pH has to equal 14, right? Okay, so we'll see that here in a minute, but okay, so everybody getting those? So here we would have neutral, right, because we have the same, which makes sense. This is what makes up KW, right, the 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7. Okay, that was the same here. Give us that. Okay, so that would be, that's neutral with a pH of 7. Okay. I want you to calculate the pH of a solution in which the hydronium concentration is 0.030. Okay, so this is pretty straightforward. So we're going to take the, get my pen out, the negative log. So you can go ahead and do that. So pH equals the negative log of hydronium concentration, or H+. So if I take the negative log of 0.030, that doesn't look like a 3. Okay. What did you all get? Yes, and you always report pH to 2 decimal places. So you don't have to look at sig figs or whatnot. You just always report it to 5.2 or whatever it is. If it's 12.25, you always report to 2 decimals. So easy enough there. Okay, had this problem said the HCl concentration is 0.030, okay, that still means the hydronium concentration, because it's a strong acid, is 0.030, right? Okay, so if we know 1, so I meant to pull this up earlier. So we found the pH is equal to 1.52. Okay, how could we find the hydroxide concentration? If we know 1, we can always find the other, right? Okay, so how could we do this? Yeah, exactly. Okay, so we're going to take our 1.0 times 10 to the negative 14, divide it by 0.030 to give us hydroxide. Okay, so this is what we did right here. And we get 3.33 times 10 to the negative 15. That's molarity, it's concentration. Okay, and then to get POH, what formula will we use? There is, we're going to talk about in a minute. Okay. To get POH, we really could do two things, but we could go ahead and just take the negative log of the number that we just got, right? So if we take POH equals the negative log of hydroxide concentration, so that's what we just found, and we get 12.48. Okay. If you wanted to, and you'll find with these problems that, especially with your homework, and we'll go through one, that there's really sometimes, more than one way to get to the answer. So you could have also just said, well, if my pH is 1.52, and I know the two added together has to be 14, then 14 minus 1.52 gives you 12.48, right? Does everybody see that? Okay. Yep. So this right here, POH plus pH has to be 14 because that's out of your range of your scale. So if you know the pH is 1.52, then 14 minus 1.52 gives you this. Yeah, so you could have done that as well. Okay. Whoops. All right. Put things up here for a second. All right, this problem, you're given the pH, and you want to know the hydronium concentration. So what do you think we could do? This is actually just algebra, but you may have forgotten it. Okay, but if we're given the pH, how can we go from pH to finding the hydroxide concentration? So the previous problem, we were finding pH, right? So we were just taking the negative log of this and getting pH. Okay, any ideas? Okay, so if you look at your equation here, you only have two variables, right? You have one here, you have pH, and this. So if you're given pH, couldn't you plug that in? Okay, and then you have negative log of, and this is what you're trying to find. Okay, so you may or may not remember this from algebra, but I'm going to show you anyways. So we take the same equation, and we say, so let's look at, whoops, I'll push my thing here. Okay, so pH equals negative log of this. Okay, but this time we're given pH. So the pH is 4.597 equals negative log, and we'll just call this X if you want to, or hydronia, it doesn't matter. Okay. Does anybody remember how we could solve for X? Okay, if you divide by a negative log, though, What does that really mean? Everybody look at your calculator. Okay, so everybody look at your log key that you've been using. Okay, if you look behind it, most calculators, you have the writing above, if you push shift or second function. Okay, so you have your log, and then what's that function behind there? Do what? Okay, yep. So that is your anti-log. Okay, so if you rearrange, you have a negative, so you're going to have to carry that through. But all you're going to do in your calculator is push second function log. Okay, so that's going to show up as this. It does in mine anyways. To the negative, okay, that comes from here, negative pH. Okay, so all in all, this is what you're coming up with. So I'm going to show that here, even though it's just a rearrangement. It's still one you want to know. Okay, but you can't forget that negative there. Okay, you could do it for hydroxide as well. So you could take the negative POH, so if you were given that. Okay, so if we do that in our calculator, and we push our second function into log, negative 4.597, we get 2.53 times 10 to the negative fifth, I believe. Okay, so it's not a new equation, really. It's all it is a rearrangement. But if you want to see it written out, okay, push second function, or shift, whatever's on here. Okay, did parentheses come up, or do you need to make your own? Okay, put in negative. Yep, 4.597. Okay, so that negative comes from, you have a negative log, so you're going to have to take the negative there. Did you get it? Okay. Okay. So here are all the expressions. So you've got to know these, and you can, like I said, we're going to see there's different pathways for solving just using these. Doesn't matter which way you do it as long as you use one that's correct. Okay, so our first one is Kw. You've got to know it. So hydroxide times hydronium equals this number. It's a constant because water is neutral, and it produces the same concentration of both ions. Okay, our scale's out of 14. So pH plus POH has to equal 14. Okay, we saw that in that chart. If you look back at that chart we did, where you may have done a little bit of calculations with it, okay, all of it added up to 14 if you looked at both the pH and POH scale. To find the pH, you take the negative log of hydronium. The POH, take the negative log of hydroxide. So the POH goes with hydroxide, with the base. Okay? If you rearrange these, so in this scenario, you're given the pH, but you need to find the hydronium concentration. So these two are just rearrangements of this. Okay? All right, so this is a very similar problem, and actually even on your exam, the table that's on your homework, you're going to have something almost identical to that. So you're going to have to fill in the table. Usually, if students will at least even do the, practice this for 10 minutes, can do it, and everybody usually aces that part of the test. So no surprise, it's going to be a table, and then there may be some more questions like this. Okay, so let's walk through it. Okay, you've got a 0.020 molarity nitric acid solution. Okay, remember, these equations only work for strong acids and bases. Okay, you got to remember that, because we're about to look at weak. Okay, so if you look at nitric acid and you're not sure if that's strong or weak, what are you going to go look at? The table that you're given, right? And you're going to see it on there, so then you know it's strong. So you're going to, if you know it's strong, then that concentration you're given for that acid has to be 0.020. of the hydronium concentration. Okay, so even though it says calculate there, we don't really have to calculate anything for hydronium, right? Because it's already given to us. Okay, because an acid, this is a strong acid, and we know we define acids by their hydronium or H plus concentration. So our H3O plus concentration is 0.020. Okay. So on your homework, it's the same thing. I'll give you strong acids and bases, and then I tell you the molarity, and you just have to put it in the table. So there's no, that's nothing to it, really. Just bring that number down. Okay? All right, so we can go, different route here. What I'd probably do is go ahead and find my pH. Okay, so if I find the pH, I'm going to take the negative log of that number there. So if I do that, I get 1.70. Okay, so we're going to do kind of both routes that you could go through, but this is just, what I do. I go ahead and I see my pH is 1.70. I go ahead and get my POH because I know it's got to be 14 minus 1.70. So that's just personal preference. It's got to be 14 minus that. So it's got to be 12.30. So to me, that's just quick. Okay, to get hydroxide concentration, we could do two things, okay? We could do this, which honestly to me, I like this better. I don't know why, but this is what I normally do. Or we can do this, right? We can rearrange KW. Okay, so what I normally do is I just go ahead and say, okay, I've got my POH, so I'm going to take the anti-log of it, and I know it's negative. Okay, don't forget that negative there. Okay, and always remember, if you have hydroxide, it's got to go with POH. Okay, sometimes it's get them flip-flopped. Okay, so if I take that, I should get 5.01 times 10 to the negative 13 molarity. Okay, or I could have taken KW divided by my hydronium concentration, and I get, it may be off, 100th or something. I think you get 5.00 instead of 5.01. Okay, not going to be picky there. Either one's fine. Okay, so the idea here is if you know one, and you know your concentration, or you know pH, or you know something about any of these, you can find all of them. So you can find hydroxide concentration, hydronium, pH, and POH. Okay, and this is as hard as it gets for this one, so we'll do this one together. Here we have calcium hydroxide. Okay, so is this strong or weak, and is it an acid or a base? Strong base. Okay, so that's the first thing we have to identify. Okay. Its concentration is this. But what do we notice about our hydroxide concentration? Okay, if we break that down, we don't have a 1-to-1 ratio, right? We have a 1-to-2. Okay, so technically our hydroxide concentration is double that of the calcium hydroxide molarity. Okay, most times it's a 1-to-1 ratio. Okay, so in most of the acids and what we've seen. Okay, but if it's not a 1-to-1 ratio, and I'll try to give you a hint so you don't just mess up on this part, but all it means is if you have a 2 there, then your hydroxide concentration, which is what we're looking at, right? Because that's what we've got to plug in over here. Okay, it's going to be twice as much. All twice that of the molarity there. Okay, so and now we have hydroxide concentration. So there it is right here. Okay. I would just, from this point, I'm just going to go ahead and find my POH. So to do that, I'd take the negative log, 0.030. Okay. And I got 1.52, I believe. Is that what you all get? POH, remember, we found hydroxide, so we have to plug into POH. .52. Everybody got that? Okay, take the negative log of 0.030. Okay, so we have this and this. Okay, so what's one way I could find pH? I know the POH, right? So what can I do? Subtract. So I take 14 minus 1.52. So my pH equals 12.48. So it's obviously a basic solution, which makes sense because we're calcium hydroxide. Okay, and the last step, it's up to you if you want to use the rearranged equation here or if you want to use KW. Okay, so I'm just going to use this one. Okay, so we want to find hydronium concentration. So I'm going to put in my anti-log to the negative 12.48. And that's going to give me 3.31 times 10 to the negative 12 molarity. Okay, if you want to check, there's multiple ways as long as you didn't make a significant error in the beginning. You know, your pH and POH should add up to 14, which obviously did. This right here, hydronium concentration times hydroxide concentration should equal what? 1.0 times 10 to the negative 14. Okay, so that's one way you can check. So, and go back and make sure you've got the right answers there. I may have written it wrong. Yeah, I did. It's negative 13, sorry. Yep, I wrote it right one place and wrong in the other. Okay, so this is, if you have a strong acid, strong base, and you're trying to find pH, POH, hydronium concentration, hydroxide, this is what you're going to go to. So especially since we don't have Chapter 19 on the test, I'll probably add some more of these. So really with some little practice, hopefully these will be, you know, pretty straightforward on the exam. Everybody can do well on those. Okay, here's just some pH ranges, just some little basic knowledge, but different things. So, of course, fruits, soft drinks, all acidic. Of course, our stomach acid is acidic. And then it kind of goes down, so it kind of gives you an idea of some different things. Here's ammonia, so it's a pretty you know, basic 11 to 12 there. So just some general. Okay, here's the pH scale. Here's some more. So there's some chemicals on here, borax, okay, antacid, so things like Tums are going to be basic so that they will react with your stomach acid and hopefully make it feel better. Okay, coffee's on the acidic side, so kind of give you an idea of some people don't realize what things are acidic, especially people that have stomach ulcers and things like that. So a lot of foods you eat are on the acidic end there. Okay, our blood has to be, I think it's 7.16, I want to say, is maybe off by a little bit. My mind just went blank. But your blood has to be at that pH, or if there's even a small change, very small change, then your body will shut down, and basically you'll die if it changes too much. So not to be morbid, but okay. So what are we going to do when we have a weak acid and a weak base? So that's what we're going to go through now. We're going to work some problems on this. Okay, the first thing that you want to do is recognize it's weak, right? So it's not going to be on your list. So thank goodness you've got that list with you on the test. Okay, so acetic acid, carbonic acid. Acetic acid is one we talk about. It's in vinegar. I don't know. I assume people know that, but it's in vinegar. You actually, if you were either in my class or Mr. Cox's class, you would have titrated with a vinegar solution and found out the percentage of acetic acid in it. Okay, so our strong acids, strong bases, just a reminder, they have that in water, they have that single reaction arrow, okay, because everything completely ionizes. That's why we can just use these equations and plug in, because if we get 100% ionization, then we know our hydroxide and hydronium concentration. Okay, for our weak acids and bases, here's acetic acid. We have the double arrow, meaning we have an equilibrium, right? So we have reaction going this way and one going this way. More times than not, weak acids, they can even just barely dissociate. So a lot of times you're mainly producing this in solution and not a whole lot of this, okay? So these numbers can get really, really small. Okay. So another constant, yay, here, we've got Kw, and we're about to show a Ka, and this is the acidity constant. Okay. So here we have acetic acid, okay, and we know that when we came up with Kc, we took concentration of products over reactants, right? Okay, when we came up with Kw, we did the same thing, except water is 1, so we didn't include it. Okay, here, you're also not going to include water, okay, because it's considered to be 1. But we take product concentrations over reactant concentration, and water's not included, so it's just something you've got to remember. Okay, and instead of calling it K, Kc, Kw, it's called Ka, because it's going to tell us the acidity. Okay. Fortunately, most all of our acids, any common one whatsoever, even ones not so common, okay, scientists, chemists have found these values for us. They've placed them in water, and they've calculated the concentration, or they've detected the concentration. So in your book, online, anywhere you go, you can find tables. So I hand these out to my organic students because we start going into more detail. Tables of lists of hundreds of acids, and it'll already have tabulated for you what the Ka is. Okay, so that is nice. Okay, so here's the Ka of acetic acid. This is a known value, so I didn't calculate this. Okay, you have to be given these concentrations to calculate it. Is 1.8 times 10 to the negative fifth. Okay, most all of your weak acids are going to have these, exponential numbers, really small numbers. Okay, so if you're a chemist, and I had to memorize probably 300 acidity values. Okay, do you think I'm going to want to memorize it like in this scientific notation? Or would it be easier if I had to memorize something that was like 2? Yeah, this is going to be pretty hard to memorize and for us to compare, okay, because we're looking at really small numbers, okay, with different, just changing in the exponent one, maybe -4 or -6, okay. So here in a few minutes, I'm going to show you how we take Ka and put it into a form that we can it's not easy to memorize them, period, but it helps us to compare them easier, okay? Okay, so if we have any weak acid, so this is really important to us, okay? All right, it doesn't matter if you know how to write out its formula. If I tell you the acid is weak, okay, a general way to write this out is just to write HA A standing for acid, and it has to have a proton because that's what an acid is, right? Okay, we're not looking at Lewis acids at this moment. Okay, so HA, and then our equilibrium. That's super important because it doesn't completely dissociate. And it's going to form H plus this, right? There's our conjugate base. Here's the acid conjugate base. And then our proton is broken apart, okay? If you know the formula of the acid, okay, so here it's written out. So we have the acid. It's understood it's in water, okay? So you may see it written like it is right there, okay? Because Ka, the definition, is how much will it dissociate in water. Okay, when you start mixing acids in other solutions and other solvents, this changes. Okay, Ka does not stay at 1.8 times 10 to the negative 5. Okay, that's only in water. Okay, so you may see it written like this with the H2O up there, or it may be written like this with plus H2O. Okay, and you can write it as H plus or H3O plus, right? Those are the same thing. Okay, so it doesn't matter. You know, even here, if you wanted to write H3O plus, I mean, it doesn't really look balanced, but it doesn't matter. They're the same, right? Okay. The larger the Ka value, the stronger the acid. Okay, so the larger that number, that means more ions dissociated. Okay, so the more ions that you dissociate, the more acidic. Okay, so if you look here, okay, and this isn't a trick question or anything, but which acid is the most acidic? See if you can find it. Yeah, HF. So look at, remember these exponents mean they're negative, so that means the larger this number is, the smaller the number, right? Your decimal is moved over 10 places. This is a really small number. Okay, so that means that this is not a really strong acid, right? It's pretty weak if only this much of it will dissociate. Okay, so HF would be, and even though it's not a strong acid, right? It's not on your list. Okay, it's still considered weak. Okay, but compared to these, it's stronger. Okay, so you could put these in order. And then if we know, if we have a stronger acid, then the conjugate base is going to be weaker, right? Remember our relationship there? Okay, so if you put them in order, here they are. So in order of the strength there. So HF, then comes nitrous acid, then acetic, okay, then chloric, and then if you look at the conjugate base, it's going to be the opposite. Because our trend says that if you have a stronger acid, you have a weaker base. And notice how this flipped. Okay, so that's just a reminder, okay, that your conjugate acid-base pair have opposite strengths. Okay, so first I want you to write the expression. Okay, all that means is for the ionization constant. Okay, ionization constant, let me make sure. Okay, it's called acidity constant or ionization constant. Okay, so what I want you to do, HCN is your weak acid. So the first thing I want you to do is plug that into this. It's a weak acid, so you're going to have HCN, equilibrium, forms H plus Cn minus, right? Acid lost a proton. Okay, so there it is. Okay, and you can put it in water if you want to. Doesn't really matter to me. Okay, it's understood that it's in water. Okay. Okay, so if we write out Ka, what are we going to do if we want to write out our Ka for this? Okay, we're going to take reactants over product concentration or product over reactants. Product over reactants, we don't put water in there, so it may help you if you don't, write water in the equation. It's understood. Okay, so Ka is equal to H plus concentration times the cyanide concentration all over the concentration of HCN. Okay, that number right there, you didn't calculate that. That didn't come out. You don't have to just know that. That's a known value. So if you actually did this in the lab, you would get 4.0 times 10 to the negative 10. Okay? And there's no units on Ka. Okay, so we just saw that one in the table. It's a really small number, so, you know, pretty weak acid. Okay, here's the fun part. So we have a weak acid now. So earlier we found pH and pOH and hydronium concentration, everything else based on a strong acid or base. So if you know these equations, you can plug it in and you can find them. Okay, for a weak acid, okay, we're going to have to go through the ice method. Everybody loves the ice method, but you're not going to have to go through quadratic formula or anything else. It's actually pretty simple. Okay, and the first thing you're going to do, though, is you need to find the hydronium concentration. Okay, so if you look up here, you're given the pH. So you're going to still use one of these formulas. Okay, so how could we go from knowing the pH to finding hydronium concentration? Okay, this is always the first step, and this is the one that if you don't get it started, it's hard to go anywhere. Okay, can't we take pH and do our antilog right here? Okay, so we can take this, 10 to the negative 1.92. Okay. All right. So I got 0.012. Not concerned with water, so I'm not going to worry about it at this point. Okay, notice that I have chloroacetic acid. You don't have to know what the formula for that is. So you can just write the general HA. Okay, if it's a weak acid, you don't have to write out, you know, Cl2F whatever. You don't have to do that, or yeah, CH3COH. So you can just write out the general expression. Okay. So we think about the ice method. Okay. What's our initial concentration of our weak acid here? 0.115, right? Okay. Okay, and we always initially have 0 of products, correct? Okay. Okay, this is the same thing as H+. Okay. So you found this in order for you to be able to plug it in, right? Okay, so we found our H+, so now we just put it in. Everything's a 1-to-1, so that number goes across everything. So we end up, we subtract, that's a 1 there. So it asked us to find the Ka. So we take our products, and they're raised to the first power, because everything's a 1-to-1. And our Ka is 1.4 times 10 to the negative 3. Okay, first key step is you got to use this equation to find your hydronium concentration, because you're given pH, so you can do that. And then from there, you just have to plug it in. And I think for all of these, I do a 1-to-1-to-1 ratio, so they're pretty straightforward. So whatever number you plug in here, because that's what you found, right? Then it should be subtracted here, added here, and then you get your E. Okay, so this one gives you a hint to start this one off. So we'll go ahead and same type problem here. This time we're just told it's a weak acid. Monoprotic means it just has one proton on it. Okay, that's sort of important because if you had 2, then more than likely your ratio of, in your equation is not a 1-to-1. Okay, so, but here everything's going to be a 1-to-1. Okay, so we've got weak acid forms H plus that. Okay. We're given the pH, so we take 10 antilog to the negative pH, which is 2.97. I believe that equals a really small number, 0.00107. We're initially given 0.10 molarity. Okay, so we made this solution. It was 0.10 molarity moles per liter. But we know it's weak, and we know the pH, so we know it's not going to completely ionize into this. And for this acid, it's really weak. It didn't ionize very much at all, 0.00107, small number. Plug that in. So I'm just going to go ahead and square that. I ran out of room, so you got 2 of those. Okay, so you want to be sure if you're doing this now, but if not, be sure you check your answers with these and make sure you get the same thing. Okay, so no quadratic formula, nothing more complicated than just using our formula we learned earlier, plugging it in, 1-to-1 ratios, and then plugging it in for Ka, which is products over reactants, not including water. Okay, this is what I was mentioned earlier, that these Ka values are somewhat hard to look at, memorize. So you normally memorize the pKa. Okay, the pKa is the negative log of Ka. Okay, so whatever you have here, so the Ka of acetic acid is 1.8 times 10 to the negative fifth. Well, I don't know that number. I know the pKa of acetic acid is 4.76. Okay, that number is a lot easier for me to remember and for other chemists as well. Okay, but they have opposite effects or opposite relationships. So we said the larger the Ka, the more acidic, right? Because that was the more that it dissociated. Okay, here, the pKa, the lower the number, the more acidic. So you can even get negative numbers. So your really strong acids, like something like HCl, it's got a pKa of negative 11. Okay, so it's going to have a really low number. Okay, so if you take the negative log of acetic acid here, the negative log of 1.8 times 10 to the negative 5, that number, you get 4.74, and some chemists like to argue it's 6 versus 7. I don't really care. We just leave it whatever it comes out to. So, and then here we take the negative log of this number, we get a pKa of 3.14. Okay, so that's just showing you. And there's a couple more problems, pretty easy, but all right, so if we compare these two, which one's the stronger acid? Yeah, HF, definitely. Okay. That's the lower number. So the lower the pKa, the stronger. Any questions on that? Almost done. Okay, we're not going to go into this much. It's not really terribly important. It was on your homework talking about a polyprotic acid, so that means it just has more than one proton. So it could, depending on what it's reacting with, it could donate one proton and then donate another one and donate how many ever it has. So the first one that's lost is the most acidic proton. Now, which one that is, we don't really know. They're all the same, really. I mean, all three of those hydrogens on phosphoric acid are, the same. So, but anyways, it just shows you the stepwise approach. As you lose a proton, then you lose another one. So, not really too terribly important to us right now. Okay, we've already talked about this numerous times, but there are very few. This is actually the answer to why there aren't very many weak bases that we talk about, because most bases aren't soluble in water if they're weak. Okay, so to get a Ka value or get those values, we dissolve them in water, right? Okay, so ammonia will hydrogen bond with water. So it is soluble in water, and we can get its value. Okay, and so it's one of the only very few of bases that actually are soluble in water. Okay, so there's very few weak bases that we can look at or determine those. So amines is what we're talking about. This is pyridine right there. It's got the nitrogen. You just look for the nitrogen. This is ammonia. Okay, methylamine, we would have a CH3 right there, a carbon. Okay, but the main idea is this nitrogen, and technically I would want to put some lone pairs there if I was drawing the Lewis structure. Okay, some very rarely, but you can come up with pKb values, meaning the acidity constants of bases, but it's pretty pointless, really, because there's only a few of them, so you might as well just compare pKa values since you have a lot more weak acids. I mean, you have, hundreds of those, so we just use pKa instead of pKb. Okay, but if we looked at an amine, is its pKa going to be low or is it going to be high? It's going to be high, exactly, because it's a weak base, right? Okay, so it's going to have a pretty high pKa value. I think it's like 30 or something like that. Okay, so these are problems from your book, but I've got them written out here, so I've got 3 of them. Okay, the first one, actually really 2 of them are really simple, straightforward. I don't have a lot of these. There's not really any of these on the homework, so be sure you look back at these and go over the problems we went over in class. Okay, they're not going to be much different than this. Okay, this just says write a equation for the ionization of a weak acid. So, and remember, and then it says what's the special symbol for the equilibrium constant? That's here, right? We've been dealing with constants. Kc was our equilibrium constant, right? In chapter 17, and we just put an A there for acidity. Okay, so if we write out, it says write a chemical equation for a weak acid. So we just did that over there. Okay. Write the equilibrium constant expression. Okay, we take products over reactants, and then we call this Ka. That's all it's one right there. Okay. All right, we're going to skip to this one real quick. All you do here, if I give you, say I want to know the pKa, so let's say I have you come up with a Ka value, but then the question says, what's the pKa? Well, then you just have to take that Ka that you found. So we just found Kas when we went through problems. And then you just take the negative log. So these two, extremely easy. You just got to remember. So you would take the negative log of each of these numbers, okay, to give you pKa. Okay, the only issues I normally have is just people are still having calculator issues. If you're plugging in and not putting parentheses or whatever. So that's really the only issues I have. But you end up with 4.14 and 9.38. All right, so which one's the stronger acid, the first one or the second one? First one. It's lower, and then its Ka value is also larger, right? So those are exactly the trend there. Okay, if we go back here, okay, this is just like the problems we did where you had to use the ICE method, so you need to be able to recognize these problems. Okay, the first thing you're going to do is recognize that you have a weak acid, okay, and usually I'll even say the weak blank acid or whatever, okay. So you need to go through and find the Ka, just like we did. So you can look back at your notes, but I want you to take a few minutes. This is really the hardest problem in the chapter, I guess. So take a minute and see if you can figure out the Ka, just like we did on the, I think it was problem 8.7 and 8.8 in the lecture. So take a few minutes and try to figure it out. So first step is find the hydronium concentration. Has anybody done that yet? What'd you get? 0.01122. I think I just used 0.011, so we'll just go with that. Okay. Okay. So here's I, C, E. Yeah, maybe I did use the 2. I'll put the 2 there. Okay. So initially, what's our concentration of HA, our weak acid? 0.10, right? Because it tells us that. So we always have 0 and 0. Okay. This right here is the same as that, so that's what we just found, 0.0112. Everything's a 1-to-1, so if you form 0.0112 of that, then you have to lose 0.0112 of this, of our weak acid. So all you're doing is just subtracting out how much ionized. Okay? So you don't have 0.10 molarity technically because it's a weak acid, so only 0.0122 is ionized. Okay, so what do you get? 0.089, or what does that come to when you subtract that? 0.08, 0.8. Yeah, it'd be just the 9 because when you subtract, we only carry through the 2. Okay. 2. Okay. All right, so we found our equilibrium concentrations, and we know in any of our constants, just like Kc, Kw, they all have to be at equilibrium. Okay, that's the only reason that we're having to go through the ICE method is to find the equilibrium concentrations. So if we plug that in, products over reactants, final answer is, what'd you guys get? 1.4 times 10 to the negative 3. At your homework one more time just to be sure. Okay, just to get you started. So these tables, like I said, very similar to what you'll see on the exam. Okay, the first thing that you have to do is look over. Sorry, it's really small. Where's the zoom button? All right, so look at this first one real quick. If everybody will listen up for a second. We're almost done. Okay, if you have HI, so what you have to look at is that a strong acid or a strong base? Okay, I take for granted that I just know these, but you need to be sure and become familiar with your list. So HI is a strong acid, right? Okay, so that number given, 0.035 molarity, is also the concentration of what? Hydronium, exactly, or H+, because it's an acid, and that's what an acid is. Okay, what about number 2 there? Rubidium hydroxide. It's a base, and it's strong. Okay, and this whole thing is all strong and strong acids and bases, this whole worksheet. Okay, so you can use all of these over there. Okay, so it's strong, so this is just where students mess up. Okay, they will accidentally put that 0.0040 is the hydronium. Okay, no, it's the base, right? So base means hydroxide, so that 0.0040 goes over here underneath the hydroxide. And then once you know one thing, then you can find all the others, right? So that's all you're doing. The same thing really is the tables down here. So it says find all of these for the acid. Just watch and make sure you're recognizing if it's the acid or the base. If it's the acid, you take the negative log of the hydronium. And if it's the base, it's the hydroxide. You just have to be careful when you're looking at those. Okay, but those are pretty straightforward. So you have the 3 worksheets. Like I said, the one short one we did in class. Really the hardest ones are those molecular equations and the writing the net ionic equations. So practice those. No reason not to do all your homework and turn it in for 100 on Monday, or no, wait, today's Thursday, right? No, yeah, Tuesday. Okay, so turn it on Tuesday. We'll review some. I'm not really sure what all we'll do that day quite yet, but we'll review, ask questions, have lab, and then you'll have your test on Thursday, just on 2 chapters. So y'all have a great weekend. Go enjoy the weather. I wish I could today. Yeah, we'll talk about it. It'll be later. Yeah, it's not going to disappear. We'll go over it. I do. There you go. Okay.
Yeah, he's just like this time around.
So on this, do we know that we're solving? I mean, do we I don't know how to say this.
Yes.
But are we doing H3O? Do we know it's H3O plus because that is
An acid, and that's what an acid is.
So
Yeah.
H3O plus corresponds to acid, and OH corresponds to base.
OH minus scores. Yes, exactly. And the reason was in the first explanation. If you have a strong acid, it completely ionizes. So if it completely ionizes, that means whatever that number is, the concentration of this is also the concentration of this, or H3O plus. Those are the same thing. Okay, that and that are the same. That's just got water on it.
So if it was, if I was doing, so right here we solved for pH first. So if I was doing, if it was a OH, for example, I would solve for POH.
Yeah, that'd be the easiest thing to do. You take the negative log of the hydroxide, and that would give you POH. Yep.
So OH.
Yeah, you just got to recognize that acid or base, is it strong, which that whole worksheet's strong.
So this is
Yeah. Think about power of hydrogen, power of acid, power of base. Yeah.
this one.
Mm-hmm.
I just had that.
Thank you.
I'm applying for another scholarship. And I was
Okay.
wondering if you probably
Just
have
send
the
it.
same one.
Yeah.
I figured just like copy paste.
Yeah. Yeah, just send it to me, or have them send me the email. Uh-huh. Bye. Have a good weekend.